We're going to continue section 3.1, which is the fundamentals or basics of probability. We're going to learn a little bit more and work with some more formulas involving probability. So in the last video, we talked about this rule where we said if we have two mutually exclusive events, that means that they don't have anything in common, then the probability of A or B is equal to the probability of A plus the probability of B. We're going to play with this formula today in this video. One typical example involving probability is drawing cards from a deck of 52 cards. So to make sure that we understand these types of probability problems, we need to know what's inside a deck of cards. So first off, in a deck of cards, there's two colors. There's black cards and there's red cards. Half of the cards are black and half of the cards are red. So we have 26. If you take 52 and divide by 2, you'll get 26. So we have 26 red cards and 26 black cards. We also have 4 suits. So the black cards are made of 2 suits. We have the clubs and the spades. And the red cards are made of 2 suits. We have the hearts and the diamonds. I think it's important, maybe because you're going to see a lot of examples involving cards in this PowerPoint and on your homework, to write this information down if you don't already know it. So we have 4 suits: the clubs, the spades, the hearts, and the diamonds. Each suit has the same number of cards. They each have 13 cards. And if you add these 4 13s together, you'll get 52 cards. Now let's talk about what's in each suit. Each suit has the numbers 2 through 10, along with the face cards, Jack, Queen, King, and Ace. So if you count all of those, that's 13. So, for example, with the clubs cards, there's a 2 of clubs, a 3 of clubs, a 4 of clubs, and so on. There's a Jack of clubs, Queen, King, and Ace of clubs. There's also a 2 of spades, a 3 of spades, a 4 of spades. Keep going, King of spades, Ace of spades. Then a 2, 3, 4, 5, and so on of hearts, and a 2, 3, 4, 5, and so on of diamonds. All right, suppose we draw exactly one card from a deck of cards. Whenever we draw from a deck of cards, we're assuming it's our standard deck, 52 cards, no jokers, and it's well shuffled. So I'm going to draw one card from a deck of cards. What's the probability that my card is a jack? Well, we have to think about how many jacks are in a deck. If we go back real quick, we see that each suit has a jack. So there's a jack of clubs, a jack of spades, a jack of hearts, a jack of diamonds. So there's 4 cards total out of 52 that are jacks. And so our probability is 4 out of 52, which you can simplify to 1 out of 13. As a decimal, it's 0.0769. Or there's about a 7.69% chance that you draw a jack from a well-shuffled deck of cards. Now let's start over. We still have that deck of cards. All of the cards are there. If I draw one card, what's the probability the card is a jack or a queen? This is one of the first times we see the word or coming in to play here. Now, if we let A be the event we draw a jack, we said there were 4 jacks. And we're going to let B be the event we draw a queen, and there are 4 queens. Now, both of these events are mutually exclusive. You cannot have a card that's both a jack and a queen. So the probability of A or B, we just take the probability of getting a jack, which is 4 out of 52, and add it to the probability of getting a queen, which is also 4 out of 52. So this becomes 8 out of 52, which you can simplify to 2 out of 13. And if you put it in a calculator, you'll get 0.1538. So there's about a 15.38% chance that when I draw a random card from a deck, I get a jack or a queen. Okay, if we draw one card from a deck of cards, what's the probability the card is a red queen or a 5 of hearts? First off, these events, getting a red queen or a 5 of hearts, are mutually exclusive. There are no red queens that are also 5 of hearts. So all we need to do is figure out what's the probability that we would get a red queen. Now there are 4 queens, but only 2 of them are red. So the probability of getting a red queen is 2 out of 52. While the 5 of hearts, there's only 1 card that's the 5 of hearts. So the probability of getting a red queen or a 5 of hearts is just adding 2 out of 52 with 1 out of 52. And that is 3 out of 52. And if you put it in your calculator, there's about a 5.77% chance of this occurring. Let's take this difficulty up just a little bit more by adding a third possibility. So if I draw a card from a deck of cards, what's the probability the card is a 5 of hearts, a red queen, or a black card? Now again, notice that all of these events are mutually exclusive. There's no 5 of hearts, that's also a red queen, that's also a black card. So maybe pause the video and think about what you should do. Just give it a try and let's see if you get the right answer. Since they're mutually exclusive and we want to get a 5 of hearts or a red queen or a black card, this translates into addition. So there's 2 hearts cards that are, sorry, there are 2 red queens and there's 1 5 of hearts and there's 26 black cards. So we just add all those numbers up and we get 29 and we divide by 52, the total amount of cards in the deck. And it's about a 55.77% chance that we would get a 5 of hearts, a red queen, or a black card. So we saw this formula before. We said the probability of A or B is adding the probabilities as long as the events are mutually exclusive. This formula, no matter how many events you have, as long as they're all mutually exclusive, and I have the word pairwise, which means A and B are mutually exclusive, along with B and C, and if you had a 4th one, C and D, and so on. If they're all mutually exclusive, nobody has anything in common with another event, then whenever you have an or, it just becomes an addition on the outside of probability. So the probability of A or B or C is the probability of A plus the probability of B plus the probability of C. Now, in the last video, we talked about the complement of an event. So are the events A and A complement mutually exclusive? Yes, they are mutually exclusive. So that means they have nothing in common. And so the probability of A or A complement is just we add those two together, the probability of A plus the probability of A complement. What do you think the probability of A or A complement is equal to? Well, it is equal to 1 because A or A complement is the whole sample space. So the probability of the whole sample space is 1. So in other words, if I ask you, like when we roll a die, what's the probability of rolling a 4 or not rolling a 4? Well, those are your only options. So you have to roll a 4 or not a 4. So there's a 100% chance that you're either going to roll a 4 or not a 4. That's why this is equal to 1. Suppose we draw one card from a deck of cards. What's the probability it's not a jack? So we have a couple of options here. We could count how many cards are not a jack, or we could just count how many are a jack. And we can use this formula we just saw. Now you see how we said 1 is equal to the probability of A plus the probability of A complement? We could solve for the probability of A complement. We could just move the probability of A to the other side. So in other words, if you know the probability of one thing and you want to find the probability of its opposite, you just subtract it from 1. So let's go back to this problem. We know the probability of getting a jack is 4 out of 52. So to not get a jack, we could just do 1 minus 4 out of 52. Now 4 out of 52 simplifies to 1 out of 13. So it's the same thing as 1 minus 1 out of 13. You don't have to simplify it. You could do 4 out of 52. In the end, when you put it in a calculator, you're still going to get 0.923 or about a 92.3% chance of getting a card that's not a jack. And if I ever go too fast, remember you can always pause the video, go back a little bit, and copy down any notes that you need to make on a sheet of paper. So suppose we flip a coin 2 times. What's the probability we do not flip 2 heads? Now, in the last video, we saw this problem where we flip 2 heads, and we said that probability was 1 out of 4. So here is A is the event we flip 2 heads. That probability is 1 out of 4. Now, the probability we do not flip 2 heads is 1 minus this 1 out of 4 because the complement of flipping 2 heads is not flipping 2 heads. So we get 3 out of 4, or 0.75. Let's go back to a deck of cards. Suppose we draw one card from a deck of cards. What's the probability the card is a jack or a spades? Now notice here is the first time we have a situation where our events, drawing a jack and drawing a spades, are not mutually exclusive. There is a card in common, the jack of spades. So we have to be careful. That formula we had before, where whenever we have the word or becomes addition, does not work exactly well here. It's the same formula, but we have to subtract something. So this is an example of 2 events that are not mutually exclusive. The addition rule for disjoint events does not apply here. And this shouldn't be here like hearing, it should be H-E-R-E like here. Is there another formula we can use? Yes. So I just want to make sure you understand what mutually exclusive and not mutually exclusive is. So we said mutually exclusive means these 2 sets, A and B, do not intersect. Let's see if we can tell the difference between or and. So if I was to, in the top Venn diagram, if I was to shade A or B, what would I shade? Okay, so I would shade everything that lives in A and also lives in B. So in the first Venn diagram, I've shaded A or B. Now let's shade in the second Venn diagram A and B. So A and B means I live in A and I also live in B. Where is that? So the middle part is A and B. Okay? Let's play with this A and B before we look at the formula for 2 events not being mutually exclusive. We need to make sure we understand or versus and. So here we have the set S, which is 1 through 10. This is our sample space. And I have A, B, and D, these 3 sets here. Can you write out what lives in A and B? So we use, when I say and, it's an upside down U. So take a second, pause the video, and write what lives in A and B. All right, nothing lives in A and B. A and B are mutually exclusive. But what about A and D? The number 2 lives in both A and D. So again, if it was a regular U, we would just be joining the sets together. But when it's an upside down U, that means and, it means it has to be something living in both sets. What lives in D and B? So the elements 7 and 8 both live in B and D. If we were to join B with D, so that would be B or D, we would have 1, 2, 7, 8, 10. That's B or D. Okay, here is the general addition rule. Given any 2 sets, A and B, in a sample space, the probability of A or B is the probability of A plus the probability of B but we need to subtract the intersection, the probability of A and B. This is the new part. So in the past, we had this formula without this, this piece highlighted or circled in purple. When the sets are mutually exclusive, this probability is equal to 0 and it disappears. So we were playing with a easier version of the rule to get used to the addition rule, and now we're going to make it a little more complicated with this subtraction. So let's see some examples. Suppose we draw one card from a deck of cards. What's the probability the card is a jack or a spades? All right. The probability that we get a jack or a spades is the probability we get a jack plus the probability we get a spades minus the probability of a jack and spades. There are 4 out of 52 cards that are jacks. There are 13 out of 52 cards that are spades. There's one card that's both a jack and a spades, and that's the jack of spades. So we're going to add 4 plus 13, and then we're going to subtract 1, because what happens is if we didn't subtract that 1, we double counted that 1. We counted the jack of spades both in the jack and also in the spades. And that's why we need to subtract. We're trying to get rid of that thing we double counted. So we end up with 16 out of 52. Let's try another one. If we draw one card from a deck of cards, what's the probability the card is a red card or a 4? So are these mutually exclusive events? No. There are 2 cards that are both 4s and that are red. So if I wanted to use the addition rule for a red card or a 4, I would count how many cards are red. That's half the deck, or 26 out of 52. How many cards are 4? There's 4 out of 52. But then in those red cards, I'm counting 2 red 4s. And also in the 4 cards, I'm counting 2 red 4s. So I have to subtract those 2 red 4s because I double counted them. So I end up with 28 out of 52. Suppose you roll a 6-sided die twice. How many elements are in the sample space? Well, let's think about it. This is sort of like that situation where we were flipping the coin twice, and we got a tails, 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 heads, heads, tails, tail, heads, heads. So we had 4 options, right? Because for each time we flipped the coin, we had 2 options. So, but this time is a little more complicated because when we roll a die, we have 6 options for the first roll, and we have 6 options for the second roll. So I could get, for example, a 1, 1, but then I could also get a 1, 2, and then I could get a 1, 3, a 1, 4, a 1, 5, a 1, 6. But my first roll could have been a 2, and my second roll could be a 1, so I could get a 2, 1, a 2, 2, a 2, 3, and 2. So if I tried to list them all out, which I've done here, I've listed all the different options. And the reason I'm putting them in parentheses and with a comma is so that you don't get 1, 1 confused with the number 11, or 1, 2 confused with the number 12. This is rolling a die twice. So in the parentheses, I have my first roll, comma, my second roll. So as you can see, I have 36 different ways that I can roll a 6-sided die twice. That's already a lot to write down. Is there a quicker way to come up with how many elements are in the space? So we may not want to have to list everything. Instead, we just want to know how many there are. And there is a quick way to do it. So what you want to think about is there's 2 rolls, and each roll has 6 options. The first roll has 6 options. The second roll has 6 options. So we just multiply 6 with 6 and we get 36. And that's how many elements are in the sample space. Okay, so we know how many are in the sample space. Suppose we roll a 6-sided die twice and A is the event, both rolls are a 4. What do you think the probability of A is? So the probability of A, we have to go back and look how many of these have two rolls being a 4. On the fourth row, in the fourth column, we see 4, 4. There's only 1 out of 36 different options for a 4, 4. So if A is the event both rolls are a 4, the probability is 1 out of 36. Let B be the event the first roll is a 3. So you're rolling a 6-sided die and you want the event that the first roll is a 3. Okay? How many different options do we have where the first roll is a 3? Well, I've listed them all here. We could get a 3 and then a 1, a 3 and a 2, 3 and a 3, 3, 4, 3, 5, 3, 6. There's 6 options. So there's 6 options out of 36. This simplifies to 1 out of 6. So that's the probability. Let's try another one. You're going to roll a 6-sided die twice. Let B be the event that the sum of the two rolls is a 10. Can you figure out all of the different ways that I can get two rolls and that the sum of those two rolls is a 10? Pause the video and see if you can write out all of those different outcomes. Well, the different ways to get a sum of 10 is I could roll a 5 and a 5, or I could roll a 4 and a 6, and then a 6 and a 4. I couldn't roll a 3 and a 7 because 7 is not an option when I roll a 6-sided die. So there's 3 out of 36 ways, which simplifies to 1 out of 12. Again, for your homework, I will probably just give you decimals, and you just need to find the decimal. So you don't have to really worry too much if you're not very good at simplifying fractions. That's not a big worry here. You just want to be able to get the decimal. Okay, let C be the event that the sum of the two rolls is greater than or equal to 10. Can you figure out the probability of C? Pause the video and see if you can find this probability. So we have greater than or equal to 10. So it could be 10, could be 11, could be 12. Those are our options here. So the 3 that we had before work, along with 5 and 6, that makes 11. 6 and 5, that makes 11. And 6 and 6, that makes 12. So there are 6 different ways out of 36, which is 1 out of 6. Let A be the event that the first roll is a 3, and B be the event that the second roll is odd. What is this probability? Probability of A and B. Okay, so we want the first roll to be 3 and the second roll to be odd. That means I have a 3 the first roll, and then the second roll could be a 1. A 3 on the first roll, the second roll is a 3, and the 3 on the first roll, the second roll is a 5. There's only 3 ways to do that. 3 out of 36, which simplifies to 1 out of 12. Now, is there a quicker way to find all the possibilities without listing everything out? So we've done this where we've listed everything out in the past few examples, but sometimes it's a little tricky, especially if there's a lot of different options to list everything out. Can we get there quicker? And there is a way. So these events, when we roll a 6-sided die twice, we call these events A and B independent. That's because what I got on my first roll doesn't influence my second roll. So when one doesn't influence the other, then we call the events independent. Now, independent is not the same thing as mutually exclusive. Mutually exclusive means they don't have anything in common. But like these events, rolling a 3 and the second roll being odd, 3 is odd. So they do have something in common. But these are different rolls. The first roll is a 3 and the second roll is odd. When we have independent events, two events A and B are independent, then we have this special rule. So we had a rule with mutually exclusive events and it involved or. And or became addition. Here, and becomes multiplication. So if you have independent events, the probability of A and B is equal to the probability of A times the probability of B. So for example, if A is the event, the first roll is a 3, and B is the event that the second roll is odd, and we're rolling this six-sided die twice, what's the probability of A and B? Well, we focus, so first off, we ask ourselves, are these events independent? Does one influence the other? If not, the first roll, the probability of the first roll being a 3 is I just focus on the first roll, it's 1 out of 6. I'm rolling a die, there's only one number, that's a 3 out of 6. The second roll, the first roll has already happened, so I don't think about it anymore, I'm just thinking about the second roll. And there's 3 out of 6 ways to get an odd number. So now we multiply those two together to get 3 out of 36, which is 1 out of 12. So there is 1 divided by 12 is the probability, and it's exactly the same thing we found before. What I'm going to do is I'm going to stop the video here, and then we'll pick this up in the next video.